For nearly 3 decades, Provinet Solutions has been providing solutions you can trust. Hello everyone, my name is Frank Mizuka, and I am the marketing specialist here at Provinet Solutions. Welcome to Wi-Fi 101. Our webinar will begin shortly. Before it does, I would like to give you a description of Provinet Solutions, introduce our presenters, and also let you know if you have any questions today, please submit them via the Questions tab. We'll be happy to answer them as soon as the webinar concludes. Here is a brief description of Provinet Solutions. Here at Provinet, we can provide the resources and services you need to succeed. Whether it's a single project or full-time on-site work, we partner with you to assess your needs and deliver a customized solution so your company can be free to focus on your mission and core values. It's now time to introduce our presenters. Our first presenter is Matt Rivard. Matt's title is Network Engineer. Matt takes care of keeping our clients and our wired and wireless networks running, while also performing upgrades and break fixes for clients and here at Provinet. Our next presenter is Tim Baker. Tim Baker is our Solutions Architect here at Provinet Solutions. Tim has been with Provinet over 15 years. Tim engineers, implements, and supports distributed network deployments, Wi-Fi systems, and much, much more. Without further ado, I would like to turn it over to Matt and Tim for Wi-Fi 101. Thank you again for joining us. And remember, when the webinar is over, we'll be more than happy to answer any questions you have. Thank you.
Welcome to Wi-Fi 101. Today we're going to talk about some of Wi-Fi's history, the fundamentals of good design, and some of the equipment that you can find out there in the marketplace today. So we'll start off talking about Wi-Fi's history. Back in the 1990s, companies wanted to start communicating wirelessly and have the mobility that wireless provides in the workplace. Several manufacturers started looking at different ways to accomplish this, and the IEEE developed the 802.11 specification, basically to make it so that different manufacturers could all have interoperable devices. Whether I bought a device from Linksys and wanted to talk to something that Intel made, we needed kind of a standard that everyone could adhere to in order to make sure that things worked. The first set of standards came out in 1999. They're called 802.11a and 802.11b. 802.11a was technologically superior. It focused on the 5 gigahertz band and allowed us speeds up to 54 megabits per second. Again, these use 20 megahertz channels, and we'll get into some of what all that means and try not to be too technical. But you should know that really 802.11a was the first standard that was agreed upon, and in many ways it was a good specification and technologically superior to the other one that came out at the same time called 802.11b. 802.11b used the 2.4 gigahertz band, but it only allowed up to 11 megabits per second. The good thing about 802.11b, and ultimately why it kind of became the de facto specification that everyone used, was because the electronics were cheaper and it made it more affordable for people to start deploying wireless networks.
A few years later, in 2003, the 802.11g standard came out, still on the 2.4 gigahertz platform, still used a 20 megahertz channel stream. However, it was able to talk at a much higher rate of 54 megabytes per second.
2009, we got the 802.11n specification. Again, this operated in 2.4 gigahertz, but also added the 5 gigahertz spectrum into the same protocol standard. The big change was that we added 40 megahertz wide channels, so basically we made the lane of our highway wider, and we also added 4 spatial streams, meaning we added more lanes to the highway. By doing that, we got up to about 600 megabits per second as our max speed.
In 2013, a new standard came out called 802.11ac. This also ran on both the 2.4 and 5 gigahertz frequency ranges, except they made the lanes of the highway even wider at 160 megahertz channel spacing. It also allowed 8 special streams, which is actually 8 lanes of traffic going down the highway, which allowed speeds up to 3.4 gigabits per second.
So the latest standard that's coming out either very late 2018 or in early 2019 is 802.11ax. In many ways, 802.11ax is similar to 802.11ac. We still have 160 megahertz wide channels and 8 spatial streams. However, some improvements in the efficiency of how they use that space ultimately should bring those speeds up to 10 gigabit or even faster.
So all these wireless devices use radio frequency, which, as we know, radio frequencies are all governed by the Federal Communications Commissions. They are the ones that specify what is and what is not allowed to be used through the airwaves. The FCC allocates a certain block of frequencies for the use in the United States. Wi-Fi operates in an unlicensed frequency range. The ranges for Wi-Fi are generally referred to as the 2.4 and 5 gigahertz based on the RF spectrum that they use. Wi-Fi is half duplex communication, means that only one side can talk at one time. So when one side talks, the other side has to listen, finish listening before it can talk back again. This is similar to like CB radios. You know, if you're familiar with those from back in the day, they're not as prominent as they used to be. But we used to have CB clubs down, where I'm at. But communication can also get garbled when too many people try to talk at the same time. So we use channels, RF channels, which are specified frequencies, to break up those frequencies to allow multiple devices to talk at the same time, as long as they were on different channels. Again, this is very similar to the way CB radios worked.
We're going to start by talking about the 2.4 gigahertz range. Basically, the FCC says this starts at 2400 megahertz and goes all the way up to 2472 megahertz. What's important to know here is that we need channels that don't overlap with each other. In 2.4 gigahertz in the United States, we basically have 11 channels that are available for Wi-Fi's use, but only 3 of those channels don't overlap with each other. If we try to use channels 2, and those are called channels 1, 6, and 11. If we try to use channel 2 or 7 or anything else, then it's going to interfere with the other ones because that frequency overlaps with each other. We don't want to do that because that slows our networks down, and ultimately we want those networks to run as fast and as reliable as possible. So when you design a network, you always want to look at channels 1, 6, and 11 in the 2.4 gigahertz range because they won't interfere with each other. The other thing that you need to know about 2.4 gigahertz is that it's heavily used by a variety of other non-Wi-Fi devices. This could include Bluetooth, operates in 2.4 gigahertz, a lot of baby monitors, cordless phones, a lot of different audio devices out there today also use that frequency band that's unlicensed. So those can also have an interfering effect that could potentially, at best case, slow down your network, or in some cases, they can actually disrupt your wireless network altogether.
That's why we use a process called channel staggering when we set up wireless networks. So you want to make sure that access points that are broadcasting radio frequencies aren't broadcasting all on the same channel in the same area. It'd kind of be like listening to 5 or 6 different radio frequencies, like on your radio in your car, listening to 5 or 6 channels at the same time. You're not going to be able to hear your favorite song because there's so much noise over the top of it. So we stagger the frequencies and channels as you see here. The blues can't talk to the blues, and they're all on channel 1. The oranges on channel 11 can't talk to each other either, and the greens in channel 6 can't talk to each other. So that means you'll get the clearest signal from the closest access point to you without as much interference as if they were all on the same channel.
One of the problems with 2.4 gigahertz was, quite honestly, we don't have enough channel space in order to stagger the channels like we would want to, especially when you get into buildings that have multiple stories and stuff. When we get into that, it's just very hard to stagger those channels to where communication takes place efficiently. That's where 5 gigahertz comes through. In 5 gigahertz, we have a much larger range to work with. And with 20 megahertz wide lanes, we can actually have 24 different channels instead of 3. What you'll see, though, is as we change how wide our lanes are by making a 40 megahertz wide channel or an 80 or 160 megahertz channels, it becomes increasingly more difficult for us to stagger those, similar to 2.4. So this top line would be similar to 802.11a or 802.11b or G with 20 megahertz wide channels. We have 24. But if we go to the 802.11n specification, we start with like 12 channels that we can do. Again, a still big improvement. But when we get into 802.11ac and soon to be 802.11a6, we've kind of come full circle and we're down anywhere from 2 to 6 different lanes of traffic that are very wide, but only 2 different lanes if you did a 160 megahertz wide lane of traffic, which can again lead to problems with reliability and throughput.
A little more details on the 5 gigahertz. The increased frequency range allows for larger channel widths, which offers increased speeds found in the 802.11n, the AC, and the up-and-coming 802.11ax. There's also less congestion from other Wi-Fi sources because most of the consumer-grade devices are using the 2.4 gigahertz range and not the 5. Potential interferers include radar from weather and military sources. And the channels that overlap with the radar and the military sources are called DFS, and there's special rules we have to use when we enable DFS channels. One of the downfalls of the 5 gigs is it has a little bit shorter range than 2.4 and requires more access points to gain the same amount of coverage as if you had all 2.4 gigahertz access points. 5 gigahertz is the preferred band used for all new deployments and should be the basis for any Wi-Fi refreshes, as the standards are all revolving around 5 gigahertz.
So another important aspect outside of RF is the transmission power. Again, the FCC regulates how much power we can transmit with our radios. And this is generally 100 milliwatts for 2.4 gigahertz and 200 milliwatts maximum for 5 gigahertz. Most people think, hey, crank up the volume, louder is better. They're wrong. In Wi-Fi, generally, the lower power is better. There's a couple reasons for this. One, it improves our client roaming. When we have a Wi-Fi device, such as our smartphone or tablet, and we're moving through it, our phone needs to decide which access point to talk to. When we have high transmit powers, it makes it very difficult for that phone to make a good decision on which AP to use. It also improves performance. When we're closer to the AP that we're talking to, we're going to have a clearer signal to them, and we're going to be able to hear them better, and they're going to be able to hear us better. That leads to faster throughput, so that way our data moves more easily between us and the access point. It also helps minimize interference. When we talked about that channel staggering, that kind of showed that, we want to keep those separate. If we have higher transmit powers, it's harder to separate those channels, and it leads to more noise in the environment. It also can extend the battery life of our devices. We want to, use that battery as efficiently as we can, so that way our devices stay powered up and are accessible. This is especially important when you think about things like portable phones or tablets that are used in a healthcare environment. It's very important for those to work as long as possible without having to go back to the charge bay. The other thing to know about transmit power is the devices that we carry in our pocket are limited in the size of the antenna that they have, as well as the amount of battery that they do have. So an AP could talk at the full power allowed by FCC, but our smartphone can't. Its antenna is too small, and it only has so much power that it can use for Wi-Fi. So it's important that we balance the maximum power that our iPhone or tablet can use with the maximum power that we set our APs to. What that means is we ensure that both sides can hear each other perfectly clear.
All right, a little further explanation on how the transmit power works between different devices. As you can see in this graphic, the access point is here. Let's say these devices are, like 100 feet away. The access point has enough power to broadcast all the way to the iPhones that you see here. And these are the recent iPhone 3s. And this has enough power to make it about halfway. So by decreasing the amount of power the access point has, allows the devices to stay connected to the closest one instead of trying to stay connected to the device all the way down the hall.
So it's important to make sure that you design your Wi-Fi based off of what we just talked about to make sure that your site's going to work well, that your devices are all going to work quickly and efficiently and reliably. There are various ways in which companies deploy Wi-Fi, and we're going to talk a little bit about some of the good and the bad of each model.
Okay, a few things we use when we're designing a Wi-Fi network are looking at things like what device is hooked to the network and how are they going to authenticate, which means how are they going to gain access to the network and how do we keep people that shouldn't be connected off of the network. Where are the devices going to be within your building or organization, even parking lots in different areas? Where are they going to need to function? And the other thing is, how many devices are you going to have at the same time? Because that's all relevant on what size of access points you need to put in. If you've got 10 clients, you can put a much smaller device in than if you have like 100 clients that all need to connect.
So after we develop our requirements for the Wi-Fi, we have to look at some of our constraints. Constraints could include budget. Sometimes, do we have enough money available to properly deploy our Wi-Fi that we would like to have in? We also have to look at time, when does this solution need to be in place? Are there other company initiatives that are going on that are going to rely on this Wi-Fi network? And maybe we need to hurry up and get that Wi-Fi in place so that way the company can move on with those other initiatives. We also have to think about aesthetics. Sometimes, can the APs be exposed, or is there other concerns that may be placed on the design that might restrict where we can place APs? As well as cabling. Wi-Fi is not all wireless. It does require a cable to each access point. So can we get a cable to that proposed access point location to make sure that it will function?
So once we get down to the requirements of the project or the deployment, we have to look at what's going to be required to actually do the job. First, we look at the equipment. What manufacturer and what model of access points are appropriate for each location. Then the next thing is where are they actually going to go? Where can you put the access points for two things, the best coverage and the least amount of interference to each other to make sure that the coverage is going to be adequate. And then something else to keep in mind is how is the access point going to actually be mounted? It's a little different if you have a drop ceiling versus a cinder block wall or drywall. You got to make sure that that's all accounted for when you make your design plan. And then actually back to the wireless functionality, what channels are each access point going to operate on and what channel widths would you use? The good thing is most modern Wi-Fi systems will actually take care of most of this on their own. They are intelligent enough to know that this access point is on channel 1, this access point needs to be on channel 6, or all the way down the line through all the channels through the 2.4 and the 5 gigahertz spectrum. And they're intelligent enough, for the most part, to know how much transmit power is going to be adequate to not interfere with each other. However, this does need to be monitored, and most of the time we do this with a post-deployment wireless survey that'll tell us if our coverage is adequate enough or not.
So there's really 3 different methods that I've seen companies do this. The first one is they guess. They kind of come in there and they'll say, okay, well, this is an apartment or a condo building. I think we need an AP in every single room. And that very well may be the case, but it's nothing more than just a guess. They might come in and put an AP every 50 to 60 feet. And kind of the thought is, you know what? It's better to have more APs than too few. If there's too many, then I can always just turn the transmit power down or even turn some APs off to kind of balance out the environment. The downside of this is it can be wasteful. You're potentially buying more access points and all the cabling and labor associated with that you don't really need. And so Provident, we don't really recommend this method, but have seen it out there in the market a fair amount.
Another way of determining where access points needs to go is to actually go to the location with what we refer to as an AP on a stick. There's actually an access point mounted to the top of this retractable tripod, and you actually fire it up and you measure readings and all array around it and as far as it can go, and you can actually make a pretty good model of where the best placement of the access point is going to be. You can run through specific locations like this if you're just questioning on whether one access point will be enough or 2 or 3. We do this a lot when it comes to like for instance concrete stairwells. You don't know how far the signal is going to push through the concrete wall or if it's even going to make it through at all. So we set this up to see how far through into the stairwell it goes, to see if we need to put an access point actually in the stairwell, because sometimes those are considered safe places and areas of rescue. The downside of this, though, is it requires somebody to actually come on site and do it, which can be very time consuming and it can be costly.
So the third model is what we call a predictive survey. This basically uses a specialized software, and we kind of take the floor plans for the building and we start drawing in walls, and we say, okay, this is a drywall wall, this is a concrete wall, and we take what we know about the environment and we build that into the plan. We also take the access points that we plan to use, and they're modeled inside the software to say, okay, this is what that antenna pattern should look like, and this is what we expect the transmission power to look like, and whatnot. And we can produce a reasonably accurate plan of what we expect to be the end result. We oftentimes will kind of supplement this with the AP on a stick method as well. So we can go in there and we can say, okay, let's use our software to develop this, but then let's kind of validate that in a couple spots through the AP on the stick method. What this does is it's kind of a good hybrid of a faster turnaround to get a less costly plan put together, but still with some reliable accuracy in which that we can comfortably deploy that solution to the customer site.
All right, next we're going to talk about some of the Wi-Fi equipment that we've seen throughout the years and up to what we've seen as of late. It's definitely changing and it's definitely made a lot of improvements over the years.
So the first equipment we'll talk about is what I would call consumer grade equipment. This is stuff that you'd find at most any retailer online. Pretty much you can find this stuff anywhere. It's usually, $100 or less. You might find some, models that are a little fancier that cost slightly more, but that's kind of the sweet spot for them. This here, is something that has been around since probably 2003. We still see them out there, as well as a modem from Comcast. It can be bundled into your internet service provider's offering as well. This is really, the best place for this is a small and medium-sized home. It's not really meant for anything else, but for most families in a average American home, this is probably what they have and probably suits their needs pretty well.
All right, next up we have a grade of equipment that we kind of call prosumer. They're not quite, like the basic end users, and they have these are users that have a little more technical knowledge and kind of like to expand what they're doing in their environments a little more, but not quite enterprise grade. These are devices that usually run anywhere between $100 to $500 or more. They rely on mesh technology to connect to the secondary AP. So, for instance, like one is the primary that plugs directly into your router or modem, and then it wirely broadcasts to all the others, and then it extends the networking. However, that's not always most ideal for the enterprise grade areas. You can find these like at your Amazon, your Newegg's, a lot of your online providers. They don't have the security, for instance, authentication methods found in enterprise products. So they're not always good at keeping the people you want not to access out, and sometimes can be problematic when trying to let people in. These types of setups are suitable for most large homes, but still aren't quite what we need for enterprise grade deployments.
Other equipment, and what we deploy most often here at Provident, is enterprise grade access points. So what does that mean? There's really a large selection of enterprise access points in really, when you go with manufacturers such as Aruba or Cisco, they make a bunch of different models to where you can really suit, hey, this room really needs this type of model, from how it mounts on the ceiling or the wall to how many radios it has and its antenna patterns, and there's a lot of flexibility there. One of the most important factors is it uses centralized management. So as an engineer, I want to make sure that my configuration is the same throughout the environment, so that way, when a client moves around my facility, they're getting a uniform connection and not all of a sudden be unable to authenticate or access the network. It also has the greatest flexibility for security, whether I am just doing a wide open network for guests to walk in and hop on to an unsecured network to go to the internet, to a simple pre-shared key that we see a lot of homes, or maybe we want to use our Active Directory username, password, or certificates. We can certainly do that. We can support multiple networks. We could have a separate network for our guests versus a different one for our staff. We don't have to buy extra hardware in order to do that. We can do that on the same platform that we currently have. The pricing really varies on this. It can be as simple as we go out and we buy the access points that we need, to a model where we pay a monthly fee for Wi-Fi access, kind of this as a service type model that we see with a lot of things, to adding different components into this to really make a unique solution that allows capabilities, quite honestly, that are beyond our dreams in some instances. They're just crazy what we can do nowadays with this. So this enterprise type solution, we would recommend it to anybody for an SMB all the way up into the enterprise. It's just really the different pieces of the puzzle that you bring together to really match what the customer needs.
Thank you for joining us for our presentation on Wi-Fi. We've hoped you've learned a little bit. We are going to open the lines now for any questions. And if you do have any further inquiries on our Wi-Fi, you can visit our website at www.provinet.com/Wi-Fi.